Let's take a look at example 3 together. Example 3 is a little bit of an interesting problem. I don't know if you remember at the beginning of this lecture, I said, usually we're given some sort of a constraint equation, but I think this next example we can do without a constraint equation. So I had mentioned to you that there was one example we were going to look at today where you didn't have a constraint equation, and example 3 is going to be that. Okay. So they tell us that an open top box is to be made from a 24-inch by 36-inch piece of cardboard. And you're removing a square from each corner of the box and folding up the flaps on each side. So let's draw a rectangle. I just realized my rectangle does not need to be this big. I'll shrink it down in a second. Something like this. Okay, it's not perfect. And then well, maybe I want a little bit bigger than that. And what we want to do, so they also give us the dimensions. So like this is 24 inches and this is 36 inches. Okay, and they're going to remove a square from each corner of the box. So I'm going to take my pen, I'm going to switch to a dotted line, and I'm going to draw a dotted line like this. I'm going to attempt to draw a dotted line like this. There we go. And then I'm going to copy that guy. I'm going to put the other one on this side here. And then we have a horizontal one. We have a horizontal one here. That looks too low. I have to move it up a bit. Move up. Oh my God. Still too low. I don't know what my problem is, but pretend that's a square. Okay. So you got these 4 squares over here that you're going to cut out. So you're going to cut out this square. You're going to cut out this square. You're going to cut out this square. I'm going to cut out this square. And after you do that, you're going to get a rectangular box. So maybe your box looks something like this. You got to fold up the 4 sides. So here's one side, here's another side, here's another side, and here's the last side. And you can connect the edges. So your box looks something like that. All right. So they ask us, first of all, is there any questions about how we got this box? I haven't really labeled any variables yet, but I'm about to. No. Okay. So then it says, what size square should be cut out of each corner to get a box with the maximum volume? So when they ask us what size square, we should probably label the length of the square. So I'm going to come over here. I'm going to label this side X and this side X. I'll label this side X and this side X, this side X and this side X, this side X and this side X. Does that make sense for everybody? And we want to maximize the volume. So we're going to maximize the volume. And does anyone, you guys know that the volume of a box is the length times the width times the height, right? I can see what the height is going to be. The height's going to be X. But I still need the length and the width. So if I call this side here the length right here, and I know that this entire length is 36 inches, what expression can I write down to represent this length right here? Any thoughts? What's this side right here? 36 minus 2x is what one of your classmates suggested, and I agree. Hold on, let me make it clear what I'm talking about. I'm talking about this length from here to here, and this is 36, which is the whole length minus the 2 x's that we removed. So this length here is x, and this length here is x. So I remove both of those. I have 36 minus 2x. Yes, a couple students told me that, which makes me happy. Once you see that one, I hope it's clear what this other side over here should be. That should be 24 minus 2x. So if I were to label my box, I'd have 24 minus 2x and 36 minus 2x like this. And then the equation of my volume is going to be x times 24 minus 2x times 36 minus 2x. Is there any questions about that? Can you guys see that we didn't really use a constraint equation, but we could use a constraint equation? We could have called this side of the box y and then said y plus 2x is equal to 36, and then solve for y, and then you would get this. So to me, I don't know, it seems natural to construct it like this without forcing a constraint equation, which is why I do it this way. Does that make sense? All right, so we want to multiply all this out because it's far easier to take derivatives of a polynomial than a product of factors. So this is going to be 24x minus 2x squared times 36 minus 2x. And then I need to distribute. So 24 times 36 is 864, x minus 48x squared. That's distributing this guy like this. And then for the next guy, I got to distribute these guys like that. And when I do that, I'm going to get negative 72x squared. And then I'm going to have plus 4x cubed. Okay. So this is going to give me 864x minus 120x squared plus 4x cubed. That's our volume, V of x. Now, we always, once you have that, the next step we do is want to find the critical values or critical points or critical numbers. So we gotta take the derivative. So you're going to get v prime of x is equal to 864x. Sorry, take the derivative, right? So 864 minus 240x plus 12x squared. And I need to set that equal to 0. So I'm going to set the left-hand side equal to 0. I'm going to factor out a 12 from the right-hand side. 864 divided by 12 is 72. 240 divided by 12 is 20. X, and then you have plus x squared like this. So I want to rewrite this as 12x squared minus 20x plus 72. Student asked, why did I factor out a 12? I didn't have to factor out the 12, Nick. I was trying to factor this guy. And when these numbers are so big, it's really hard to factor it. So that's why I tried to factor out the 12 to make this guy look simpler, to see if I could factor it nicely. It turns out this one doesn't factor nicely. So we're going to have to use the quadratic formula. But at least I'm working with numbers like 1, -20, and 72, not these ridiculously huge numbers, I guess. Okay. So we have to use the quadratic formula. So you have -b plus or minus square root of b squared minus 4ac all over 2a. Your a is equal to 1, your b is equal to -20, and your c is equal to 72. So when I put all of these into the quadratic formula, I'm going to get -20 plus or minus the square root of 400 minus 4 times 72 times 4 times 1 times 72. That's going to give us 288. All divided by 2a, which is just divided by 2. So that's what my x value is. So this tells me my x is really going to be, I'm sorry, this is positive 20. Negative times a negative is positive. Okay. So we get 20 plus or minus, you know, 112 over 2. And we can simplify this a little bit. 20 divided by 2 is 10, plus or minus, I think 112. 112 is divisible by 4. Yes, it is. It's divisible by 16, right? 112 divided by 16. Yes. So this is square root of 16 times 7 divided by 2. So this gives me 10 plus or minus 4 rad 7 over 2, or 10 plus or minus 2 rad 7. Ooh. Okay. So when you take your calculator and you evaluate this 10 plus 2 rad 7, that's going to give you 15.3. If you look at our original question, the longest side is 24. So if you cut out something that was 15.3, that doesn't make sense. You're going to have like no rectangle left. You'll have no box. Okay. The other value is 10 minus 2 rad 7. 10 minus 2 rad 7. And this gives you 4.7. 4.7 seems like a reasonable number. Finally, you have to make sure that this is a maximum. So I'd run the first derivative test. Your critical value is going to be 10 minus 2 rad 7. I can plug in a test point like v prime of 4, and you'd see it's increasing. I could do v prime of 5, and you'd see it's decreasing, and that means you have a max. Okay. So in the end, they wanted us to know what size square should be cut out to get maximize the volume. And the answer to that question is 10 minus 2 rad 7. Let's see what our units are, inches. Does that make sense to everybody? Is there any questions about this thus far?